Welcome to the third lecture of the video lecture series on linear algebra. Today we will talk about three sections mainly. First is algebra of subspaces, then coordinates and change of basis. Also, this will be the last lecture on the chapter on vector spaces according to our syllabus. So let's start. Now, in this theorem 1.4, this says that intersection of any subspaces of a vector space is again a subspace. So in this theorem, it says that intersection of two subspaces is again a subspace, but the same cannot be said for union of two subspaces. For example, consider the vector space of R3 over the field of real numbers and these two subsets U and W. U is the plane x plus y plus z equals to 0, and W is the plane x plus y minus z is equals to 0. Now both U and W are subspaces, but U union W is not, because the respective vectors alpha that is 1, 2, minus 3, which is coming from U, and beta that is 1, 2 and 3 coming from W are there in U union W, but the linear combination, one particular linear combination alpha plus beta, that is 2, 4, 0, this vector is not there in U union W. So therefore U union W is not a vector space for this particular chosen example. So, in our objective to make more vector spaces from the existing ones, we look at U and W as subsets of R3 and look at the subspace both of them generates, that is U union W generates. Now, by this theorem, we already know that the subspace generated by a subset is the linear span of that subset. Right, so by that theorem, it is linear span of U union W, L of U union W according to the notation we are using. Now, as U and W are also subspaces, we have a better representation of linear span of U union W. Now, L linear span of U union W, linear span of any set, is that collection of all possible linear combinations, but we have a better representation when these sets U and W both are subspaces of a vector space V. This is explored in the following theorem. It says, let V be a vector space over a field F and U and W be subspaces of V. Then the subspace generated by U and W is, obviously it is linear span of U union W. This is U plus W. And what is that set? That set is the collection of all sums of the vectors taking each from U and W. That is alpha plus beta, where the vector alpha is coming from U and beta is coming from W, and the collection of all such sums. Fine. Let's see the proof. Choose any vector U plus gamma, choose a vector gamma from U plus W, arbitrary. Then gamma is of the form alpha plus beta, where alpha is a vector from U, beta is a vector from W. Then both of these vectors alpha and beta, since they are in U and W respectively, they must be in U union W. And of course, U union W is contained in linear span of itself, right? So, therefore, gamma, since linear span of U union W is a subspace, their sum, which is a linear combination, is also there in linear span, and so therefore the vector gamma is there in the linear span of U union W as well. So therefore U plus W, which had we had chosen gamma from U plus W arbitrary, and we have shown that it belongs to linear span of U union W. So therefore U plus W must be a subset of linear span of L of linear span of U union W. Conversely, to show the other way around, that linear span is also a subset of, is also contained in U plus W, we will show that U plus W is a subspace containing both U and W. Now, as the linear span of U union W is the smallest such subspace which contains both U and W, our purpose will be served, right? This one U plus W is a subspace, and subspace containing both U and W, and linear span of U union W is the smallest subspace containing U and W. So this one, the linear span, has to be inside this one. So this is what we are going to show. Okay, so choose two vectors. We are going to show something as a subspace. So we choose two vectors and gamma 1 gamma 2, and show gamma 1 plus c gamma 2 is again in the space as well. So choose gamma 1 and gamma 2, two vectors from U plus W, and c an arbitrary scalar. Then there are vectors alpha 1 alpha 2 in U and beta 1 beta 2 in W, such that gamma 1 is represented as alpha 1 plus beta 1 and gamma 2 is alpha 2 plus beta 2. Then gamma 1 plus c times gamma 2 is alpha 1 plus c times alpha 2 plus beta 1 plus c times beta 2. So this is basically gamma 1 is alpha 1 plus beta 1, c times gamma 2 is c times alpha 2 plus beta 2, and if you using commutativity and associativity, we can always write it in this format: alpha 1 plus c alpha 2 plus beta 1 plus c beta 2, and this belongs to U plus W, because alpha 1 plus c alpha 2 belongs to U, because U is a subspace. Alpha 1 and alpha 2 are two vectors from U. C is an arbitrary scalar, so alpha 1 plus c alpha 2 is again in U. Beta 1 plus c beta 2 for the same reason belongs to W as well. Okay, this conclusion we are making because we have the information that both U and W are subspaces. That is why this alpha 1 plus c alpha 2 and beta 1 plus c beta 2, they will belong to U and W respectively, as both U and W are subspaces. Hence, by this theorem, which theorem says this necessary and sufficient condition for subspaces? This is this one. So by this theorem, U plus W is a subspace of V. Also, U can be written as U plus theta, the null vector. Okay, now U plus theta, so theta is a particular choice of vector from W. So therefore, U plus theta must be contained in U plus W, because theta is a particular choice of vector from W. Also, W, which can be written as theta plus W, and here theta is acting as the particularly chosen element from U. So U plus W contains this theta plus W as well, which is W. So U is also contained in U plus W. W is also contained in U plus W, right? As theta belongs to both of them. Of course, theta null vector belongs to every subspace. So U plus W is a subspace containing both U and W. As we said earlier, linear span of U union W is the smallest such subspace. We must have L of U union W is contained in U plus W. So consequently, combining these two, this one and this one, we have L of linear span of U union W is equal to U plus W. Fine. Now, for finite dimensional spaces, we also have the following result. So this theorem says that let V be a finite dimensional vector space over a field F, and U, W are subspaces of V. Then dimension of U plus W is dimension U plus dimension W minus dimension of U intersection W. Remember, intersection of two subspaces is again a subspace, so we can actually talk about dimension of U intersection W. Proof. If either u is contained in w or w is contained in u, then u plus w is equal to w or u respectively, and u intersection w will be u or w respectively. So u plus w will be the bigger one, the sum of these two will be the bigger one, and the intersection will be the smaller one if either of them is contained in the other. Then the theorem is actually trivially proved. You see, if u is a subspace of w, then u plus w will be w. So this is your w, dimension w, and this is dimension u plus dimension w minus this intersection will be the smaller one, in that case u. So dimension u plus dimension w minus dimension u. So you are left with w, dimension w, and here also dimension w, and the vice versa the other case. So this is trivially proved. So let us assume neither of them is contained in the other. So that means u intersection w is strictly contained in u and is strictly contained in w as well. Okay, they are proper subsets of, it is proper subset. U intersection w is a proper subset of both u and w. Now let us name the things. Dimension u as small u, dimension w as small w, and dimension of u intersection w, let us call that d. Then d will be strictly smaller than u and is strictly smaller than w as well. Let S1 alpha 1 up to alpha d be a basis of u intersection w. Okay, so we start with the basis of u intersection w, the smallest one. Then by extension theorem, this says that every basis, every finite linearly independent set is a part of is either a basis or can be extended to a basis. So that is your extension theorem. So by this extension theorem, this set, this basis S1 can be extended to basis of both u and w. Okay, let S2, that is alpha 1 to alpha d, that is coming from S1, and the newly adjoined vectors beta d plus 1, beta d plus 2 up to beta u, where u is the dimension of capital U. This is a basis of u, and S3 is alpha 1 to alpha d, that is coming from S1, and newly adjoined vectors gamma d plus 1, gamma d plus 2 up to gamma w. Okay, this is the extended basis of u and w respectively. Okay. Also, let us agree to dedicate the indices I, j and k for the alpha I vectors, beta j vectors and gamma k vectors respectively. So over here we have a collection of vectors. This alpha vectors, alpha I vectors will be denoting them by beta vectors, will be indexing them by j, and these gamma vectors we will be indexing them by k, right? So that is, unless otherwise stated, the indices I, j and k will run from, I will run from for the alpha vectors 1 to d, right? J will run from for the beta vectors from d plus 1 to u, and k will run for the gamma vectors, that is d plus 1 to w, right? So whenever we will be writing sum over I, we will mean that I is running from 1 to d. Sum over j is running from d plus 1 to u. Sum over j, that is sum over k, that is d plus 1 to w. Okay, this is just a making the notations less cluttered. Okay, fine. So we will show that the combination of all of them, this S1, S2 and S3, so these alpha vectors, the beta vectors and the gamma vectors all together, they make a basis for u plus w. Okay, so let's see. So let's choose a vector alpha from u and beta from w be arbitrary. Then for some suitable scalars, some sets of suitably chosen scalars ai dashed, bj and ck, we will have alpha is coming from U, so S2 was the basis of U, so S2 was this alpha I vectors and beta j vectors. So alpha can be written as linear combination of alpha I vectors and beta j vectors with this set of scalars ai and bj. Right, so that is what I mean over here, some sets of suitably chosen scalars. So this alpha I and bj, these the two sets of scalars are giving the representation of alpha with respect to the basis S2. And similarly for the vector beta, which is in W, so for W S3 was the basis and S3 had alpha vectors and gamma vectors in it. So beta is equals to sum over I ai dashed alpha I plus sum over k ck gamma k. Fine. So this we must get because S2 and S3 are basis of U and W respectively. Fine. So therefore if we add them, alpha plus beta will be, and we will collect these alpha I vectors, the coefficients of alpha I vectors together. So we'll be having sum over I ai plus a dashed I times alpha I plus sum over j bj times beta j plus sum over k ck times gamma k. And now you see that these alpha I vectors, beta j vectors, gamma k vectors, all of them are coming from S, the combined set. So this is a vector in the linear span of S, right? So alpha plus beta is a vector in linear span of S. So therefore U plus W is a subset of, is contained in linear span of S. Fine. The fact that the other way is also true, that is linear span of S is contained in U plus W, is guaranteed by the observation that S is contained in U plus W, right? And U plus W is a subspace. Right, because S, that was the combination of all those alpha vectors, beta vectors, gamma vectors, and they all came from either U or W. So it is contained in U plus W. Each of them you can write as a vector from U plus 0 if it is coming from U, or if it is coming from W, you can write null vector plus that vector. So every vector is there in S is contained in U plus W, and U plus W is a subspace. So linear span, so this implies linear span of S is also in U plus W. Fine. So therefore U plus W will be equal to linear span of S. So therefore S generates the subspace U plus W. So we have proved one part. Next we will show that S is linearly independent. To call remember, we want to call S a basis of U plus W. So so far we have shown that S generates U plus W. In the next step we are going to show S is linearly independent. Fine. So for sets of scalars ai, bj and ck, consider the relation this one, that sum over I ai alpha I, sum over j bj beta j, and sum over k ck gamma k is equal to null vector. Call this equation as star. Now we need to show that ai, all these vectors ai, bj and ck, all these vectors are necessarily 0. Fine. Now this star implies, if you take the sum over k, this portion to the other side, then you get sigma ai alpha I plus sigma bj beta j is equals to minus of sum over ck gamma k. Fine, no problem there. But the vectors alpha I and beta j, these vectors alpha I and beta j are coming from U, whereas gamma k vectors are coming from W, right? So therefore this double star shows that the left hand side is a vector in U. The left hand side is a vector in U and the right hand side is a vector from W. Right, since these two vectors are same, so this vector, I mean any of the representation, so this whatever vector this represents, that vector must belong to the uh, intersection of u union w, right? Let's see once again. This left hand side is my is a vector from u, because alpha I and beta j vectors are vectors from u. So this is a vector in u, and this side is a vector from v. So the same vector, since they are same, the same vector is there both in u and in v, and in w, sorry. So that means this thing must be there in the intersection of both of them, u intersection w. Since S1 is a basis of u intersection w, we get another set of scalars ai dashed again, such that minus this vector minus ck gamma k, this vector is equals to sum of ai dashed alpha I, right? S1 we started with the basis of with this basis of u intersection w. So this vector, since it is there in the intersection of both of them, u and w, it must be expressible in as a linear combination of the vectors from S1, that is sum of ai dashed alpha I. Now this implies by a change of sides, it means this sum over I ai dashed a alpha I plus sum over k ck times gamma k is equals to the null vector theta. But linear span of this one, this is triple star, not double star, sorry. The linear span of triple star is a linear combination of the vectors from S3. You see, these alpha vectors and gamma vectors, they are basis for w. So this is a linear combination of the vectors from S3. Now since S3 is a basis, this triple star implies that this relation is satisfied only when all the scalars are necessarily 0. So that is, for every I and k, ai dashed is 0, and so are ck's. All these scalars must be necessarily 0. Now replacing all the ck's by 0 in star, in this one, sigma ai alpha I star was sigma ai alpha I sigma bj beta j plus sigma ck gamma k is equals to theta. So if you replace all the ck's by 0 in that star, you get this one, sigma ai alpha I plus sigma bj beta j is equals to theta. But in this case, these vectors are from S2, right? Alpha I and beta j vectors, they are basis of u, right? S2, which we extended from S1 to be a basis of u. So these vectors are S2 coming from S2, which is again a basis. And since S2 is linearly independent, since it is a basis, for every I and j, the scalars ai and bj, all of them should be necessarily 0. So therefore star holds for only for the trivial choice of scalars ai is equals to bj is equals to ck is equals to 0. All the scalars must be necessarily 0 in order to hold the relation star, sigma ai alpha I plus sigma bj beta j plus sigma ck gamma k is equals to theta. Okay, this shows that S is linearly independent. Fine. So therefore S is a basis of u plus w. Now how many elements are there in S? So dimension of u plus w is, so S had d many alpha vectors, u minus d many beta vectors, and w minus d many gamma vectors. So those many vectors were there in S. So the dimension of u plus w is the number of elements in S, that is d plus u minus d plus w minus d. And this turns out to be u plus w minus d, and that is dimension u plus dimension w minus dimension of u intersection w. This proves the theorem. Okay, let us consider an example before we end this section. In the vector space R3 over R, consider the subspaces. We already considered earlier that U as the plane x plus y plus z equals to 0 and W as x plus y minus z equals to 0. Here dimension of U is 2, also dimension of W is also 2. Now U intersection W is this straight line passing through the origin and having the direction ratios 1, minus 1, 0. So this is the straight line C times 1, minus 1, minus 1, 0, and C is varying over R. So this straight line is the intersection of U and W. So therefore dimension of U intersection W should be 1. It's a straight line. Now U plus W is this thing, that U is x plus y plus z equals to 0. So this is, and W is x plus y minus z equals to 0. So U plus W will be sum of two elements from U and W. So x1 plus x2, y1 plus y2, z1 plus z2, where the point x1, y1, z1 is coming from U and the point x2, y2, z2 is coming from W. So therefore x1 plus y1 plus z1 should be 0 and x2 plus y2 minus z2 will also be 0. So this is my description of U plus W. This is same as I am replacing z by x and y in both cases. So this turns out to be x1 plus x2 in the x coordinate, y1 plus y2 in the y coordinate, and the z coordinate turns out to be minus x1 minus y1 because of z1 and plus x2 plus y2 because of z2. And here all these x1, x2, y1, y2 are real numbers varying over real numbers. Fine, this entire set we are talking about. Now this thing can be written as x1 into 1, 0, minus 1. See, x1 is there over here, so there is 1 here, then nothing here, so 0, and there minus 1 over here. Now x2 is there in first coordinate, so 1 over there, not there in the second coordinate, so 0 there, and x2 is there in the third coordinate, so plus 1 there. y1 is not there in the first coordinate, so 0. Y1 is there in the second coordinate, so it is plus 1. Minus y1 is there in the third coordinate, so minus 1 there. y2 is not there in first coordinate, so 0. y2 is there in the second coordinate, so 1, and y2 is there as a plus in third coordinate, so 1 here. So this vector is same as this vector. Fine. x1 plus x2, x1, x2, y1, y2, all of them are varying over R. Call this star. Then observe that out of these four vectors 1 0 minus 1, 1 0 1, 0 1 minus 1 and 0 1 1, out of these four vectors this last vector 0 1 1 can be written as minus 1 times the first vector, plus 1 times the second vector, and plus 1 times the third vector. So see, minus 1 plus 1 0, so it makes it 0 in the first coordinate. Minus 0 plus 1, so makes it 1 over here. And lastly minus minus plus 1, plus 1, 2, minus 1, that is 1, so 1 here. So this vector, the fourth vector, is linear combination of the first three vectors. And these vectors, what we have written here, the 1 0 minus 1, 1 0 1 and 0 1 minus 1 are linearly independent. So therefore star, this relation reduces to x1, this is just a regrouping according to this one, according to this relation. This is x1 minus x2 times the vector 1 0 minus 1, x2 plus y2 times the vector 1 0 1, and y1 plus y2 times the vector 0 1 minus 1. And this x1 x2 y1 y2 are varying over R. So this means that we can basically these are basically dummy variables, x1 x2 y1 y2. These are dummy variables. Let us replace them by another set of dummy variables x y z. So this is x times this vector 1 0 minus 1, y times 1 0 1, and z times 0 1 minus 1, where x y z are varying over R. And this is nothing but R3. Okay, a three-dimensional subspace of R3, that means it is R3. So therefore, dimension of u plus w minus dimension of u intersection w. So dimension of u was 2, dimension of w was 2, dimension of u intersection w was 1. So this one is 2 plus 2 minus 1, that is 3, and that is indeed the dimension of u plus w as well. So this finishes the section on algebra of subspaces. So next section is on coordinates. So let's start. Major convenience of the concept of dimension is the fact that there exists only one vector space of a particular finite dimension under a fixed field. Okay, we will explore this fact when we study linear transformations. In this section, let us explore another convenience we enjoy by fixing a basis of a given vector space, the coordinates of a vector. Consider this point P 1 2 in R2. Fine. Geometrically speaking, the coordinates 1 and 2 are the distances of the point P along the x and y axis respectively. Linear algebra, being an algebraic tool to study the geometry of Rn in general, establishes a whole new interpretation to the coordinates. Let us see the consequence in the general setup. Let V be an n-dimensional vector space over a field F. Let B, script B, equal to alpha 1 to alpha n be a basis of V. Let alpha be any arbitrary vector of V. Then there exist scalars C1 to Cn such that alpha is represented as a linear combination of these vectors alpha 1 to alpha n. So now if there is any other expression of alpha in terms of the basis vector alpha 1 to alpha n, say alpha equals to d1 alpha 1 plus d2 alpha 2 up to dn alpha n, then we will have if we subtract one from the other, then we have theta in the left hand side, and clubbing the coordinates vector wise in the right hand side, we have c1 minus d1 times alpha 1 plus c2 minus d2 times alpha 2 up to plus cn minus dn times alpha n. Hence, by the linear independence of the basis B, we will have all these scalars should be necessarily 0. C1 minus D1 will be 0, C2 minus D2 will be 0, C3 minus D3 and so on up to Cn minus Dn, all of them will be 0. So that means C1 equal to D1, C2 equal to D2 and Cn up to Cn equal to Dn. So in a finite dimensional vector space, given a basis, the set of scalars representing a vector is unique. A natural question arises at this point. Can we represent a vector in terms of the scalars? Let us dig a little bit more into this matter. If we consider the set of scalars as sets, then there is a problem. Suppose alpha 1, alpha 2 is a basis of V. Now just like the points 1, 2 and 2, 1 in R2, the vectors represented by C1 alpha 1 plus C2 alpha 2 and C2 alpha 1 plus C1 alpha 2 are also different. Okay, the point 1, 2 and 2, 1, these 2 points are different points in R2. So as similarly, the vectors B1, which is same as C1 alpha 1 plus C2 alpha 2, and B2, which is C2 alpha 1 plus C1 alpha 2, these two are also different vectors, of course. But observe that both of these vectors beta 1 and beta 2 have been generated by same set of scalars C1, C2. So to remove this ambiguity, we need to impose some kind of order. We impose that on the basis and call it an ordered basis. So an ordered basis, so alpha 1, alpha 2 and alpha 2, alpha 1 are not same. Essentially, we consider the vectors in an ordered basis as terms of a finite sequence and not as elements of a set. Okay, they are terms of a sequence, so they come in a particular order. Some comes first, then second, then third, and so on. So they're this order. So they're as terms of a sequence and not as elements of a set. This maneuver helps us in what we want to achieve. Before proceeding, let us record the formal definition of ordered basis, which is, let V be a finite dimensional vector space over a field F, and the ordered basis of V is a finite sequence of vectors which are linearly independent and spans V, which is a basis which has a an order defined on it. Okay, so let B be an ordered basis of V, and alpha from is any arbitrary vector from V. Then there exist unique scalars. By our earlier discussion, there exist unique scalars C1 to Cn from F such that alpha is equals to C1 alpha 1 plus C2 alpha 2 up to Cn alpha n. Therefore, there is a one-to-one correspondence between alpha and this n tuple C1, C2 up to Cn. This n tuple C1 up to C1, C2 up to Cn, this is a tuple, n tuple in Fn, which is a vector space over the same field F. We already had introduced this one in the example of vector spaces when we had the first lecture. So this one is an element of the vector space Fn. Then, by the definitions of the vector addition and external scalar multiplication in Fn, that is coordinate wise addition and scalar multiplication. Okay, that is right, like this one, coordinate wise addition and scalar multiplication. For any two vectors alpha beta in V, where alpha corresponds to C1 C2 up to Cn, these scalars, and beta corresponds to D1 D2 up to Dn, these scalars considered as points in Fn, we have alpha plus beta is equals to alpha is C1 alpha 1 plus C2 alpha 2 up to Cn alpha n. Beta is D1 alpha 1 plus D2 alpha 2 up to Dn alpha n, according to this rule, right? So then, clubbing the scalars vector wise, we have C1 plus D1 times alpha 1, C2 plus D2 up times alpha 2, and up to Cn plus Dn up to alpha n. So this one corresponds to, now this one corresponds to the vectors C1 plus D1, C2 plus D2 up to Cn plus Dn in the vector space Fn. So, and that is according to the rules of addition in Fn, this is same as the sum of the points C1 up to Cn and D1 up to Dn, right? So, and for any scalar x in F, we have x times alpha is equals to x times C1 alpha 1 plus C2 alpha 2 up to Cn alpha n. Then this is x times C1 alpha 1 plus x times C2 alpha 2 up to x times Cn alpha n, which corresponds to this vector xc1 xc2 up to xcn, this point in Fn, and which is same as x times c1 up to cn, this point. For the vector alpha in V, so this shows that the sum of alpha and V, the addition operation in V corresponds exactly to the addition operation in Fn. The external scalar multiplication in A by a scalar corresponds to external scalar multiplication in Fn by the same scalar, right? So for the vector alpha in V, call this vector C1 C2 up to Cn, this point in Fn, the coordinates of alpha with respect to the ordered basis B. Remember, we need to fix the basis first before we move to any discussion of this sort. Then the above discussion says that we can express and carry out the algebra in V in terms of coordinates of its vectors. In R2, if we fix our ordered basis as 1 0 and 0 1, then the coordinate 1 0 and 0 1, that is the unit vector along x-axis and y-axis respectively, then the coordinates of the vector whose tip sits at the point 1 2 are 1 and 2. right? So this is the so at first we had this 1 2 as the geometrical representation of the distances along x-axis and y-axis respectively, and over here we are imposing an algebraic interpretation of the coordinates, right? So this, if we choose this as our standard basis 1 0 and 0 1, then the coordinates of the vector whose tip sits at the point 1 2 are 1 and 2. Fine. If this example still baffles your mind, consider the vector space R2 cross 2 over R, the set of all matrices. Okay, we also introduced this one in the examples of vector spaces in the first lecture. So consider the vector 1 2 3 4, this matrix 1 2 3 4. Let us choose the ordered basis R of R2 cross 2b 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. This is the standard canonical basis of the vector space R2 cross 2. Then the vector 1 2 3 4 can be written as 1 times this one 1 0 0 0, 2 times this one 0 1 0 0 0 0, 3 times this one 0 1 0 0 0 1 0, and 4 times the last one 0 0 0 1. So this corresponds to the coordinates 1 2 3 4 in R4. So the coordinates of this vector in the form of matrix in the vector space R2 cross 2 is same as R. The coordinates are 1 2 3 4. This point in the vector space R4. So 1 2 3 4 are the coordinates of the vector space of the vector matrix vector 1 2 3 4 in R2 cross 2. So this concludes our section on coordinates. So let us move to the last section of change of basis. So far we had fixed an ordered basis and carried out our vector operations in terms of the coordinates. But there is no fixed rule for choosing a particular basis in general. Although we have the concept of standard ordered basis for vector spaces like Rn, R, M cross n, and few others, a detailed discussion on the general situation proves to be worthwhile. A brief motivation quoted from Hoffman-Kunz is worthy of reading. One might wonder at this point why we do not simply select some ordered basis for V and describe each other in V by its corresponding n tuple of coordinates, since we would then have the convenience of operating with only with n tuples. This would affect our purpose for two reasons. First, as our axiomatic definition of vector space indicates, we are attempting to learn to reason with vector spaces as abstract algebraic systems. Second, even in those situations in which we use coordinates, the significant results follow from our ability to change the coordinate system, that is, to change the ordered basis. Frequently, it will be more convenient for us to use the coordinate matrix of a vector relative to the ordered basis B. Okay, that is x equals to the column matrix x1, x2 up to xn, rather than the n tuple x1, xn of coordinates. Now, one thing, let me tell you very informally, that this column vector is actually the way we should be writing coordinates. Okay, but why do we have this habit of writing them in this horizontal way? For a very practical reason. If we write it in this way, in this column way, it takes more space. That's it. It takes more space and it makes very bad design for the text to appear in the book. That is the only sole reason why we choose to write in this horizontal format. Otherwise, in its purest form, it is always written and it should be written in the column vector form. Okay, fine. So after that agreement, let us move. So let B1 alpha 1 to alpha n and B2 beta 1 to beta n be two ordered bases of V. Let alpha be any arbitrary vector from V. Borrowing the notation from this Hoffman-Kunz, let us agree to denote by square bracket suffix 1 as the coordinate matrix of alpha with respect to the basis 1, B1, A1 to A, and coordinates of alpha with respect to the second basis as B1 to Bn. Okay, the coordinate matrix of alpha with respect to basis B1 and B2 respectively. Then alpha, which it will be A1 alpha 1 plus A2 alpha 2 up to An alpha n, and it will be same as B1 beta 1 plus B2 beta 2 up to Bn beta n. That is how we define the coordinates in the last section. Fine. So now, as B1 is a basis, the vectors for vectors beta j, there exist unique scalars Pij such that beta j is equals to P1j alpha 1 plus P2j alpha 2 plus up to Pnj alpha n, where j is running from 1 to n. Okay, here also we are dedicating the j index for beta vectors, I index for the alpha vectors. Now I would ask you to do this thing by yourself, because just by reading or listening to the video, it is not very advisable to understand in this way. Instead, do it by yourself. So write it down this way: beta j as the collection of as this way, I represent it in this way: P1j alpha 1, P2j alpha 2, and this way Pnj alpha n. This j corresponds to this beta j vector. And in notation, this is I equal to 1 to n Pij alpha I. Okay, as I said, I index is for the I vector, alpha vectors. Sorry. Fine. Therefore, alpha 1, A1 alpha 1 plus A2 alpha 2 up to An alpha n, the alpha vector, is this one. Is just written in notation, so sigma notation is equal to alpha is equal to, again, this one b1 beta 1 plus b2 bn beta n is equals to this one bj summation of bj beta j. Fine. Now this is beta j, again, as we came across over there, this is same as every beta j vector is same as sum over I, Pij, the scalar, times alpha I vector. Now this one, by commutativity of the summations, I comes first, then comes j. J comes first and then sum on I. So j runs from 1 to n, Pij bj, the times alpha I, and then everything sum over I. So hence, by uniqueness of linear combination, now you compare these two, this one over here, and this one. Okay, both of them are are expressions of alpha with respect to the same set of scalars, alpha I, here also alpha I, right? So they must be same, all of them individually. So we must have alpha I is equals to, no, this must be ai, I'm very sorry, this will be ai is equals to this portion. Okay, this is the coefficient for alpha I in this expression, and ai is the coefficient of alpha I in this expression, left hand side. So ai, I'll change this one in the PDF uploaded. We must have ai is equals to sum over j Pij bj for every I running from 1 to n. In terms of the coordinate matrix, we will have, this turns out that coordinates of alpha with respect to the first basis 1 is p times the coordinate of alpha with respect to the second basis, where p is this matrix Pij. Okay, this is the uh, row wise row wise multiplication of this Pij into the vector column coordinate column vector alpha b column vector actually. Fine. Since there is a one-to-one correspondence between a vector and its coordinates, we must have this shows that one-to-one correspondence between a vector and its coordinates. We must have this coordinates of alpha with respect to the first basis is 0 if and only if the coordinates of the same vector with respect to the second basis is also 0, the null vector actually. 0 0 0 0, that 0 vector in Fn. That is the system of linear equations Px is equals to 0 admits only trivial solution. Okay, hence P has to be an invertible matrix. Therefore we get this alpha with respect to the coordinates of alpha with respect to the first basis is same as P times the coordinate matrix of alpha with respect to the second basis, and the other way around, that is coordinate matrix of alpha with respect to the second basis is equals to P inverse, the inverse matrix of P times the coordinates of alpha with respect to the first basis. In other words, we have proved the following theorem. Let V be a finite dimensional vector space over a field F, and let B1 and B2 be two ordered bases of V. Then there is a unique necessarily invertible n cross n matrix P such that for every vector alpha in V, the coordinates of alpha with respect to B1 is equals to P times coordinates of alpha with respect to basis 2, and coordinates of alpha with respect to second basis is equals to inverse matrix of P times the coordinates of alpha with respect to basis 1, where jth column of P is Pj and Pj is the coefficient matrix of beta j with respect to the first basis. Okay, that is what we get from this relation over here. Ai is equals to sum over j Pij Bj. This one corresponds to this conclusion over here, that jth column of P is Pj times Pj is equals to the coefficient of beta j with respect to the first ordered basis B1. The converse of the last theorem is also true and easy to prove. It is, let V be a finite dimensional vector space over a field F, and B1 be an ordered basis of V if P is an n by n invertible matrix over F. Then there exists a unique ordered basis B2 such that for every vector alpha in V, the coefficient matrix of alpha with respect to the first basis is equals to P times coefficient of matrix of alpha with respect to the second basis, and the other way around. Coefficient matrix of alpha with respect to the second basis is equal to the inverse matrix of P times coefficient matrix of alpha with respect to the first basis. An immediate corollary to the last theorem is this. Let F be a field and let alpha, which is A1 to An in Fn. If B is the standard ordered basis of Fn, that is B is equals to E1, E2 up to En, where Ei is a point in Fn, so Ei has in components Ei1, Ei2 up to Ein, and jth component of Ei is 1 if j is equal to I, otherwise 0. Okay, so Kronecker delta this situation. So that is the standard order basis of Fn. Then the coordinate matrix of alpha with respect to B is given by this notation, square matrix, square bracket A suffix B is the coordinates of alpha, this A1, A2 up to An. So this finishes the chapter, the section on change of basis, and also the chapter on vector spaces. The next chapter is on linear transformation. The first video I had made earlier on this chapter was on rank nullity theorem. So the link is up here. I'm adding that video over here. To maintain the continuity, though, I here have copied the notes from that video, this video over here, with the current one, and have given the link to the entire PDF. So thank you for your patience, and we'll see you in the next video.